feel. Lay on the out and out, preaching words and verbs and academic sermons. Come along with me, take my hand and do some learning.
Welcome. Let's do some math. This is the first of 3 videos which will offer the briefest of surveys on the pure mathematical field of analysis. Now, huge disclaimer, this is certainly not a complete examination of analysis. There will only be 3 short videos on it, and they're mostly meant to give a rough idea on the subject. Moreover, if you have any appreciable training in analysis, then this video probably has little information that is new to you. However, if you are someone who has not had the opportunity to take an analysis class, but you're open to the terrifying prospect of
learning new math,
then this video is right up your galley. And with that, we transition into our first topic of this video, which is the Greeks, who used galleys to traverse the Mediterranean. You see what I did there? I'm like, this will be right up your galley, and then, okay, here we go. So one of the coolest groups in mathematical history are, in my opinion, the Pythagoreans. Why were they so cool? Well, in short, because they were a mathematical cult. The cult of Pythagoras is thought to have been established circa 530 BC, or for all you history nerds who know enough to know the difference, BCE. Members of this order were well known in their day for things such as vegetarianism, belief in reincarnation, and a religious dedication to the study of mathematics. At the time, Greek mathematicians believed that all numbers were rational numbers. Now, what are the rational numbers? Let's start with what the integers are. The integers are simply the set of numbers such as 0, 1, -1, 2, -2, 3, -3, and so on. The rational numbers are ratios of these. We use the symbol Q to stand for quotient. So here we'll have some a divided by b, where a and b are integers, and b is not 0. So the Greeks thought all numbers were of this form, a ratio of integers. Things such as 3 divided by 7, or 1,000,002 divided by 372,521, or things like this. In general, if you think in terms of a decimal expansion, they are numbers with a decimal expansion that at some point repeats, such as the decimal expansion 45, 45, 45, etc. And as long as that 45 keeps repeating, we might write as 0.45 with a bar over to indicate it's repeating. That's actually the same number as 45 over 99. Now, it was the Pythagoreans who discovered that, sadly, but interestingly, not all numbers are actually rational. Let's consider the following. Suppose we have a square and the length of each side is 1. Now, if we consider the diagonal of this square, we can compute the length of this using something also attributable to the Pythagoreans, namely the Pythagorean theorem. This tells us that x is going to be the square root of 2. You might be aware that this is not a rational number, and even if you are, however, what's interesting here is how it was shown to be irrational. If irrational is not something that rings a bell to you, or even if you've heard it before but would like a little review, let's talk about what irrational is. An irrational number is simply a real number that is not rational. For the sake of notation, let's specify that the sets we're looking at here are z, the integers, where z stands for Zahlen, which means number in German. The rational numbers, where we choose q to mean quotient. The real numbers, which are the set that is the primary focus of real analysis, or sometimes just called analysis, and the irrational numbers. Together, the rational numbers and the irrational numbers make up the real numbers. In some sense, a good way to think about this is that the rational numbers are in some way deficient, and by adding in the irrational numbers, you complete them in some way to get the real numbers. So how did the Pythagoreans show that square root of 2 is irrational? They used mathematical proof. You may have seen this briefly in some of your computational mathematics courses, but chances are that if you're watching this video, then you haven't seen very much of it, or maybe even any at all. So what is the concept? A mathematical proof is a series of statements that work from a set of mathematical axioms and premises to reach a logical conclusion. Each of these statements should follow logically from one another, and it should be that if both the reader and the writer understand the rules of logic and all the other mathematical ingredients, that the argument is completely convincing. For example, we'll look at the logical argument that the square root of 2 is irrational. Here we'll use the proof technique of proof by contradiction. This is a technique where we assume the opposite of what we're trying to show, and then show that that assumption leads to some contradiction. If we're trying to show that the square root of 2 is irrational and we're using contradiction, we'll assume that the square root of 2 is rational. If we assume square root of 2 is rational, then we know we can write it in a given form, namely as one integer divided by another. Now we could have a rational number of the form, let's say 8 divided by 4. But let's suppose that we have a rational number that's already in reduced terms. If it isn't already, we could just cancel out like terms in the numerator and denominator until we get down to a number that is in reduced terms. Now, before we go further, let's number our steps just to make it easier to keep track of. And now we'll do some algebraic manipulation of our formula here, that is square root of 2 is equal to a divided by b. This is the same as saying a is equal to square root of 2 times b. Then we can square both sides, getting a squared is equal to 2 times b squared. And now let us consider the possible cases for a. In the first case, let's suppose that a is even. That means that a is equal to 2m, where m is some integer. If we substitute that into our formula here, what we end up with is 4m squared is equal to 2b squared. We can divide by 2, giving us 2m squared is equal to b squared. Now consider all the possibilities for b. Again, b can be even or odd. If b is odd and you square an odd number, you'll get an odd number. So if b were odd, b squared would also be odd, but that's not what we have over here. No matter what m is, doesn't matter because it gets multiplied by 2, which means that this is an even number over here. Therefore, it cannot be that b is an odd number. We conclude that b is even. Now, what's the problem here? So a being even and b being even contradicts this assumption. Now, in the case where a is odd, we would have that a is equal to 2m plus 1, where m is again some integer. Doing the substitution into this formula, again, what we would get is, and now we can see the problem is that on the left-hand side, we have an odd number. On the right-hand side, we have an even number. This can't possibly happen, so that means it can't be that a is odd. We showed that a cannot be even, that a cannot be odd, so a can't be anything. But that's a problem because we assume that a was some integer. And every integer has to be either even or odd. Therefore, in every single case, we reach a contradiction. That means that it is not possible for square root of 2 to be rational, leaving that it must be irrational. Now, this is pretty cool in of itself, but here the story gets a little weird. The Pythagoreans were, by many accounts, a quite secretive group. They initially kept this discovery secret, wishing to preserve the mystical notion that all numbers are ratios of integers. But eventually, a member of the group by the name of Hippasus of Metapontum revealed this secret to the Greek world. And the Pythagoreans celebrated the fact that their mathematical discovery could further advance the knowledge of humanity, and no, I'm kidding. The Pythagoreans took Hippasus out into the ocean and they drowned him. Now, the Pythagoreans were far from the only Greek philosophers of the time whose thoughts would eventually find their way into modern analysis. The Greek philosopher Zeno is credited with a set of paradox given the lazy name of Zenos Paradoxes. One such paradox involves the notion of whether it is possible to actually, say, cross a room. Suppose you're 2 meters from a door. You're feeling pretty confident that you can walk that 2 meters. In fact, you're so confident you give it your all, you happen to cover 1 meter in 1 second. Keeping up your brisk speed, you cross half the remaining distance, 1/2 meter, and you do that in 1/2 second. You cross half of that remaining distance, which is 1/4 meter, and it takes you 1/4 second. So you stop and think first, wow, I'm good at walking. And 2, how long is this going to take me? I have to do an infinite number of things if I keep having the distance from me to the door. How long will this take? Let's take a look and add up all the time it'll take to get the door. We know that the first 1 meter was covered in 1 second. Then the next 1/2 meter was covered in 1/2 second. The following 1/4 meter was covered in 1/4 second, and so on. Calling the total time t, what we get is something known as an infinite sum. And if we add all this time up, it'll end up being that the total time is 2 seconds. In some sense, it's surprising that we can do something that takes an infinite number of steps, each time having our distance, but let's say taking smaller and smaller steps forward. And somehow this infinite number of things can be done in a finite amount of time, a very finite amount of time, in fact, just 2 seconds. Now let's see what happens if we just make a slight adjustment here. Suppose now that we have the same situation where we're walking to a door and the first 1 meter takes 1 second, the next half meter takes a half second, but now, as opposed to the previous case where the following 1/4 meter would take 1/4 second, it now takes a little bit longer, it takes 1/3 second. Then the following 1/8 meter would take 1/4 second, and so on and so forth. So the question is, how long does it now take the person to reach the door, doing, in a way, the same number of infinite steps, crossing the first 1 meter, then the next 1/2 meter, and then the next 1/4 meter, and so on, taking the exact same size of step? How long will it take in this case? And the answer is,
it'll take forever.
So why is this true? Well, let's first agree on the following fact. If you have a different sum of an infinite number of things, such as the infinite sum where we just add up 1/2 to itself over and over and over, it may not be hard to intuitively see that this will add up quote unquote to infinity. Now, the reason I've put this in big quotes is infinity itself is not a real number. It's a concept. It's sort of like friendship. Did you ever think about it? Friendship is not a real thing that we can touch. It doesn't, exist in any physical sense. It's just a concept in our minds. So the next time someone says,
I'm so glad that we're friends,
you can say,
friendship's not real, Jimmy. Duh.
So what does this have to do with this infinite sum? Well, we say it's infinity, quote unquote, because we can take this sum to be as large as we want just by adding up enough of the terms. For example, if you want this sum to be bigger than 1, okay, well, simply add up the first 3 terms. Do you want it to be bigger than, let's say, 1.3? Fine. Then add up the first 4 terms. That would give you 2, which is bigger than 1.3. Do you want it to be bigger than, let's say, 100? Fine. Add up the first 201 terms. That would give you 100.5. So as large of a number as we can come up with, a positive real number, we can get this sum to be larger than that number just by taking enough sums to begin with and adding those up. And then we'll still have more left over afterwards. If that ever happens, we say that this is equal to infinity. Now we'll remove the block quotes now that we've talked about what it means to use this notation. As far as this relates to this time that we're trying to find, let's consider this. T is certainly equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus a 6th plus a 7th plus 1/8. Notice that 1 plus 1/2 plus 1/2 is 1. 1/2 is, of course, 1/2. So at this point, these two sums are equal. Now looking at the next terms, we have 1/2 in T sub 1, and then we have 1/3 plus 1/4. But notice 1/3 is bigger than 1/4. If 1/3 is bigger than a 4th, if you add 1/3 plus 1/4, you get something that's larger than a half because you're adding up 1/4 plus 1/4, which is a half. And this part is bigger, giving you a sum bigger than a half. And over here, we have that 1/7 is larger than 1/8. We have that 1/6 is larger than 1/8. And we have that 1/5 is larger than 1/8. And now if you take this sum of 4 things, since they're each larger than 1/8 or they're equal, their sum will be bigger than 1/2. That means that we can take T and we can always add 1/2 more to a partial sum. If we start with 1, we can add another half and get 1 plus a half. We want it to be larger than that, we can add yet another half. That is a half and then some, because 1/3 will be slightly larger than 1/4. Then we want to add another half. We can at least guarantee we'll get that high by adding all of these terms here, where we've added at least another half there. In the same way as we talked about with this sum, we can get this one to be as large as we want it to be, which means that it will also be equal to infinity. So the amount of time it takes someone to cross the room, if they modify their speeds, as we mentioned here, that amount of time will be an infinite amount of time. Now let's
take it to the limit.
First, consider the circle of radius 1. Now, if I ask you what the area of the circle is, chances are you could either just say it from memory, or you could look it up on Google and say, here's a formula. Now, that formula wasn't always known. Somebody had to come up with it. Supposing you don't know the area of the circle, how might you find this out? Let's suppose that you only know how to find the area of something simple like a triangle. Here might be a way that you could get the area of a circle, which is very non-triangle-like, by first considering triangles that are both inside the circle and outside. If we do the calculations here, we'll end up with an area for the triangle in gold of approximately 1.299. The area of the triangle in blue is approximately 5.196. Now we know that the actual area of the circle is in fact pi 3.14 approximately. These values are not great estimates, but though they aren't great estimates to start with, let's see what happens when we look at something like a pentagon. Now, I don't claim these to be perfect pentagons, even though I want their sides to all be of the same length. But since I'm drawing it by hand, it's not going to be exact. However, we can see the main point in that when we take pentagons as opposed to triangles, we've already covered a lot more area, both inside the circle, leaving only this area here uncounted, and there is less area outside of the circle that we're overcounting. Taking this to more of an extreme, let's say we take a n-gon where n is equal to 10. Okay, this 10-sided n-gon really went off the rails, but I think it illustrates the point. By taking regular n-gons where all the sides are the same length and increasing the number of sides, we get something that's closer and closer to a circle. All the while, these geometric shapes are relatively easy to find the area of, because each one can be broken down into triangles. And triangles are easy to find the area of. Now, I know I've been talking a lot about the Greeks, but...
Please, I can change.
Now, let's talk about Bhaskara, namely Bhaskara II. Bhaskara has an awesome moniker. He's known as Bhaskara the Teacher. I mean, how cool is that?
Hey, do you know Bhaskara?
Yeah, isn't he the guy that's a teacher?
No, not a teacher. He's like the teacher.
It's like being known as like the professor, which is so cool. Actually, there is someone, a trick basketball player called the professor. He's actually pretty fun to watch. But it's like, you know, your boxing nickname.
This corner, we have Bhaskara, the teacher.
Yeah, boy. I hope you brought a backpack, because I'm going to take you to school.
So what is Bhaskara II known for? He's considered the greatest Indian mathematician of all time, and not least of which among his accomplishments are working on fundamental concepts of analysis for over 500 years before both Newton and Leibniz.
Now, how about that?
In particular, Bhaskara is credited with being the first person to discover differential calculus. Let's look at the central idea. So suppose you're driving a car that's going continuously forward, you don't reverse, and your position at time 1, let's say t1, is position, let's say y1. To give a specific example, we'll say that at 0 seconds, we are at position 5 meters. Then at some later time, let's say t1 plus h, where h is equal to 3600 seconds, that's an hour, and the position we'll call y2, and say that is 93,600 meters. Now our average speed can be calculated by seeing what our change in position is over the change in time, which amounts to 26 meters a second approximately, and that's about 60 miles per hour. Now the chance that you maintain exactly that speed the entire time is pretty unlikely. Maybe someone tried to pass you, you got competitive and sped up to try to get in front of them because
Forget that.
Someone's trying to pass you? No way.
Then there are other times where you're checking the scenery and maybe you slowed down intentionally, just enjoying the view. Either way, the calculation we did was an average speed. However, let's say we want to know what our exact speed is at any given moment. Well, we can check something called the speedometer. The speedometer will tell us exactly at a single moment how fast we're going, and that's changing all the time. Let's put this in terms of a mathematical function. If we graph this, we have this parabola here. Now suppose we want to know if we're at this exact point, 1, 1, what will be the change as we go from this point to another point? That is, let's say the point 2, 4. Now I purposely left the term change ambiguous. There are different types of changes. For example, we can look at the change in the x direction. Sometimes we denote that by this delta x. Then we can look at the change in the y direction, denoted delta y. Now clearly we can compute these changes. The change in x is just 1 unit, and the change in y is simply 3 units. But let's say we would like to know at this exact moment what the change is. Like, what is the slope? For example, we can find a slope from these 2 points, red to blue. Drawing a line through these 2 points, we then note that the slope is simply the rise over the run. And in this particular case, the rise over the run of the purple line is going to be 3 divided by 1. Now, if we look between the red point and let's say this white point, which is the origin, if we look at the line that's passing through that point, the rise over the run in that case will be a rise of 1 over a run of 1. So the slope is equal to 1. But if we want to know the slope of the line giving the instantaneous change at this red point, that's clearly not going to be as steep as the purple line or as shallow as the white line. For example, let me roughly draw in this line, which is called the tangent line. And in particular, it's the tangent line to the function f at the given value of x is equal to 1. Now it's less than a slope of 2, it's more than a slope of 1. Maybe it's around 2, but it could be a variety of things. So let's see if we can't try to more accurately determine what it is besides just guessing. And to do that, let me blow up this picture. And by blow up, I don't mean destroy it, I mean increase it in size so that we can better see what's going on. So here we have the green curve representing y is equal to x squared. We have the 2 points in red and blue as earlier. And we have a thinner version so that we can draw more lines of the purple line going between the red and blue point. Now this line does have a name, the purple line, as did the white line in the previous diagram. These are called the secant lines through these 2 points. Let's consider some other secant lines. If we were to consider a point here and look at the secant line, it might look something like this, where this corresponds to an x value of, say, 3/2. Slope here is 5/2. And let's draw in the tangent line to the function f at the point where x is equal to 1 and see how these secant line slopes are matching up. We can see just in a geometric sense that the secant line here has a steeper slope than the tangent line. So too does this secant line in yellow. And if we were to consider a point even closer, let's say a darker blue, we might get a slope that's even closer. Now, I don't want to ruin what the actual slope is. I want to give you a chance to try to figure it out on your own, but I'll give you a hint. It's not 7. With that, I hope you enjoyed this video and learned a few things. We'll see you in the next video.